Okay. All right. That's a slightly different function. Okay. All right. Well, good morning. And so today I am going to start on the extra credit topics from chapter 9. It's in your interest to do them in terms of credit, because it's extra credit, but it's also in your interest to do them if you need to take any other chemistry in the future, because some of the topics in chapter 9 are topics that get covered in future courses. Okay. So let's start. This is called chapter 9, which is Chemical Bonding 2. So what we've done so far, chapter 8 is almost completely dedicated to the idea of Lewis structures, right? So chapter 8 is Lewis structures. So it's this idea that you have an atom and it has pairs of electrons that it is sharing with other atoms and may have, let's do a different symbol here. I'll put X there. And that these other atoms also have pairs of electrons. For example, in the case of B, they would have what we call lone pairs, right? And so we used the octet rule. We looked at some exceptions to the octet rule. We looked at bond enthalpies, the strength of the bonds. But it's essentially based on the idea of these dots and these lines, which represent pairs of electrons. Now what we're going to do is we're going to look at a couple of ideas. The first one is the idea of what we call geometry. So we'll cover that today. And then tomorrow what we'll do is we'll look at 9.2, which is, we'll come back to this issue of polarity. Okay, so we'll cover those two topics over the next couple of days. So let's start with geometry. Lewis structures are not a theory or a technique that tells you the geometry, the shape of the molecule. Lewis structures can tell you the arrangement of electrons, the arrangement of valence electrons in an atom and in a molecule or an ion. But it doesn't tell you explicitly what the structure, meaning the arrangement of the atoms are. So for those of you that are biology majors, you understand that the arrangement of atoms is very important in terms of biochemical activity. There are these very complicated molecules called enzymes, and enzymes, the arrangement of the atoms, how they are related to each other geometrically or geographically, if you want to use that term, that affects how they're able to react. So they've evolved over time to allow certain ions to go through cell membranes, but not other ions, right? So geometry is an important issue in terms of chemical reactivity. So in particular, in terms of biochemistry. So we're going to look at some basic shapes. So when you hear the term geometry, just think shapes of molecules. And what we can say about it is that the geometry of the shapes of these molecules and ions is related. We can use the Lewis structure as a starting point. So we use Lewis structures as a starting point. Okay. And then what we're going to do is we're going to use the Lewis structures as a starting point, and then we're going to implement something called the, I'm going to write it out, Valence-Shell Electron-Pair Repulsion Theory. That's a mouthful. Valence-Shell Electron-Pair Repulsion Theory. So what we do in order to make that easier to say is we just do the acronym. So we're going to call this VSEPR theory. And then typically it's pronounced Vesper. Just so it's easier to say, okay? So Vesper theory is Valence-Shell, Electron-Pair, Repulsion theory. Now, Vesper theory is based on really a very simple idea, maybe two simple ideas. One is that electrons do have a tendency to form pairs. So a chemical bond between two atoms, this is a pair of electrons. Right? We also have this idea of a lone pair, right? A lone pair or a non-bonding pair is a pair of electrons. And even when there are more than two electrons holding atoms together, those electrons still tend to form pairs. So even if we have a triple bond between two atoms, all that means is that we have 3 pairs of electrons. And again, the reason behind that is quantum mechanical, right? If you have an orbital, whatever kind of orbital you want it to be, a 1s, a 2s, a 2p, a 3d, a 4f, whatever type of orbital it is, the Pauli exclusion principle holds that we can have a maximum of 2 electrons in that orbital. And one has to be spin up, which again, remember, that means that ms is plus a half, and the other one has to be spin down, which means that ms has got to be minus a half, right? But they form pairs, and there is a tendency for electrons to form pairs, okay? So in a chemical bond, we'll talk a little bit more about this when we get to more advanced ideas. In a chemical bond, we're going to assume that that's what's happening, that this pair of electrons, we're not going to talk about what type of orbital it is right now, but we'll say that that orbital has room for 2 electrons. So it's spin up, spin down, and that's why bonds typically are pairs of electrons. There is some evidence that some bonds are 1 electron or maybe 3 electrons. It does happen, but they're relatively rare. Most bonds, the vast majority of bonds, are pairs of electrons, okay? 1 pair, 2 pair, 3 pair. All right. So now let's talk a little bit about the electron. The electron is this fascinating particle. And if you think about it, when you take chemistry, we talk a lot about the electron. Most of our understanding of the electron is very recent historically. In my office, I have a chemistry textbook, a general chemistry textbook from 1921, which is 100 years ago this year, right? The electron is mentioned 1 time in that entire textbook. And that's because the electron had just been discovered by physicists only maybe 15 years earlier. And even chemists did not even really talk about the electron. They understood the idea of electrolysis. They understood the idea that the atom was somehow electrically charged, but physics had not worked its way into the chemical nomenclature. So the electron is essentially not even mentioned in this textbook. Compare that to a textbook today where almost every chapter talks about the electron, right? So we talked about the electron in terms of redox chemistry. We talked about the electron in terms of the planetary or the nuclear model of the atom. It's this particle spinning around the nucleus. So we had different symbols for it even, right? And then we said, no, the electron, which might be represented as an E negative, is actually this wave. It's a wave that's somehow around the nucleus, right? So it has wave-like properties. And then we said, well, actually, we can represent the electron by using a dot, that's a useful method for representing this electron. And so what we're going to talk about right now is the tendency or the behavior of the electron when it forms a pair, when there are two of them bound together. And we're going to call these pairs of electrons. So a pair of electrons, which we could represent this way, or we could represent this way. Okay. Now, in order to talk about geometry, to talk about shape, again, we're talking about the shape of a molecule. What we're going to do is we're going to identify, the first step is to identify what are called electron domains. Okay, electron domains. Here's the key to this. An electron domain is a region of space that possesses pairs of electrons. Around the central atom. We're only going to consider the central atom. Central. So remember when we did Lewis structures, we said we have a central atom, and the central atom will form bonds to surrounding atoms. That's what we're talking about here. The central atom is this A here. Now, when you do the Alex problems, Alex is going to use a slightly different nomenclature. They're going to say it's AX instead of B, which is fine, AX, right? And we're going to represent molecules in the following way. We'll call this AX3, right? So we have the central atom, A, and then we have 1, 2, 3 surrounding atoms. So we would call that AX3, okay? Now the goal to get to geometry, or the step to get to geometry, is to first count what we call electron domains around the central atom. Okay, so here's your central atom, or here's your central atom. How many electron domains are around that central atom? So let me show you how we count these. So this is how you count electron domains. So I'm going to show you with an example. So the bond there is a single bond, right? You can see that's a single bond. So a single bond, which we represent with a line, right? That counts as one electron domain. Okay, that counts as one. If we have a double bond, that also counts as one. So a double bond. That counts as a electron domain. If we have a triple bond, that counts as an electron domain. And if we have a lone pair, that counts as one electron domain. So be careful. When you're going through these problems, make sure that you don't count a double bond as 2 electron domains or a triple bond as 3 electron domains. A double bond is 1 and a triple bond is 1. Now here's the logic behind this. The logic is, even though there are 3 pairs of electrons in this triple bond, so that's 3 pairs, right? They all are in the same region of space, meaning that all of those electrons are located in one direction. They're all pointing between the A and the X. So they're not taking up 3 regions of space. They're taking up 1 region of space. Same with a double bond. that double bond, even though it has two pairs, is only taking up one region of space between those two atoms. Okay, so that's the reason that a double bond is 1 and a triple bond is 1. Now, here's step 2. Electron domains repel each other and move away from each other as much as is geometrically possible. Okay, so be careful. The terminology here is important. Electron domains repel each other, not electron pairs, right? So we're not claiming that this pair is going to repel this one. We're claiming that this domain here is going to repel this domain here. And they will move away from each other as far as possible. Okay? So let me show you an example. So this is, a structure. So we have a central atom A and three surrounding atoms X. Okay, so this is AX3. So what we're claiming, in fact, I can even put a double bond here. I'll put a double bond on that one just so you can see it that way. Okay. What we're claiming is that these three domains, right? There's three of them around the central atom. You've got one here, a single bond counts as 1. A double bond counts as 1, and a single bond counts as 1. They're going to repel each other, and they're going to move as far away from each other as they possibly can. The argument is essentially, the logic is that electrons repel each other because they're negatively charged. But if they're forming pairs, they don't repel each other enough to move away from each other because they're in the same orbital. So these domains will move away from each other. So what will happen is they will move as far away from each other as they can. Okay, so I tried to show you a picture of that, right? A drawing, a diagram, that these three electron domains are now about as far apart from each other as they can be, right? So we're really talking about geometry. If three items are moving around a center and getting as far away from each other as they possibly can, how far apart will they be? That's a geometric question that has to do with space, right? And it turns out the answer is best measured in terms of angles, right? We're talking about trigonometry, essentially. The furthest that three surrounding atoms can be away from each other, we're not going to use distance, we're going to use angles, is 120 degrees, a third of a circle, right? And so you end up with this little triangle, right? If you think about it, you have a little triangle. And our angles here are 120, okay? So what we're going to do is I'm going to go through a list, the geometric response to how far apart are they going to be, depending on how many electron domains we have. So let me show you. So I'm going to put the number of electron domains. Actually, let me rewrite that. I'm going to take up a little more space over here. So number of electron domains and then we're going to do the angle. Sometimes there's more than one. And then a diagram, just to show you. Okay. So If you have only one domain around the central atom, there is no answer to that one. So what I mean by that is this. If you have a central atom and there's only one domain coming off, so let me do it this way. Okay. Essentially what you get is a straight line, right? So we're going to call this linear. It's a straight line. You just get a straight line. Okay. Now, if you have two electron domains, now we have something that's kind of interesting. The angle ends up being 180 degrees. So what I mean by that would be something like this. So there's two domains coming off the central atom, right? What's going to happen is they're going to move as far apart as they can. And geometrically, the furthest apart they can move is on opposite sides of the atom, as far away as they can. So that's 180 degrees. All right, it's half a circle. If you think about it like a circle, if you go from here to here, that's 180. You go from here to here, that's another 180. So all the way around is 360. Okay, so essentially you're pivoting from one domain to the next. Notice I didn't put any surrounding atoms there. I'm going to ignore the surrounding atoms for now. We'll come back to them in a little while. And this is also called linear. It's a straight line. So meaning that these bonds are directly across from each other. So the whole shape is a straight line. We call that linear. Now, if we have three domains, we did that one a little bit earlier, it's 120. And so now notice that it's starting to take up more space, right? Because now I'm using 2 dimensions. When you only do 1 dimension linear, that doesn't take up much room. But when you do 2 dimensions like this one, that takes up more space. Okay, so this is 120 degrees from one domain. Again, it doesn't matter whether it's a single, double, or triple bond or a lone pair. We're just looking at the angles between these electron domains. This has a special name. It's called Trigonal Planar. You got to memorize that name. Trigonal, like a triangle, but trigonal, planar. Plane means flat. Like a piece of paper is a plane. So if I take this piece of paper here, it's flat. That's a plane, right? So that's called a plane surface. Now, if I roll it, it's no longer a plane, right? Now it's 3-dimensional. But a plane is actually just 2-dimensional. So the reason it's called trigonal planar is because it's a plane, it's flat, but it's also triagonal in shape. Okay, so it's a flat triangle, which we call a trigonal planar. Now you get up to 4, and now something interesting happens. The angle is 109.5 degrees, and now it becomes 3-dimensional. So that means we have to use a different notation for drawing it. So here's what I'm going to do. I'm going to draw a line this way, and then a line coming off this way. So those are 2 of the lone pairs. I'm sorry, those are 2 of the electron domains. And then I'm going to use what's called a wedge notation. So I'm going to put a little solid wedge here. So this wedge is representing an electron domain. It could be a lone pair, it could be a single bond, it could be a double bond, it could be a triple bond, but it's an electron domain. And then what I'm going to do is I'm going to use what's called a dashed line notation to represent the 4th. Remember, we have 4 electron domains. So 1, 2, 3, 4. Now here's the notation. The notation works like this. This is coming out of the plane. Okay, so it's coming out of this whiteboard that I'm drawing on. And when you use this dash notation, it's going into the plane of the whiteboard. So let me see if I can show you maybe something that could kind of help you see what I mean by that. So imagine that the central atom is at the center of these two pins. Okay, it's right at the center. So from your perspective, okay, there we go. This one on the top is coming toward you, right? So this is directly towards you. This is somewhat towards you. This one here is completely away from you. Here it's somewhat away from you, right? So towards you, away from you, somewhat away from you, somewhat toward you. So the notation here is that this solid wedge is coming a little bit towards you, and the dashed wedge is moving a little ways away from you. And so this is three-dimensional, and it's called a tetrahedral arrangement. And the angle is 109.5. Okay? This is, again, caused by the repulsion of these electron domains. And for now, what we're claiming is the electron domains could be a lone pair, a single bond, a double bond, or a triple bond, right? But these electron domains are moving away from each other as far as they can. And these angles and shapes reflect how far away they can get from each other. Notice the angle's getting smaller. Why is it getting smaller? It's getting smaller because there's more of them. And if there are more of them, they can't be as far apart, right? If you only have two, you can be really far apart. But if you have three, now they have to be closer to each other, right? Because there's more of them to fit into space. So this is your trigonal planar right here. It's like a little triangle, right? But it's flat. Once you get up to tetrahedral, now they're pretty close to each other in a sense, right? They get closer and closer. So this is a little bit, let me get this down. This is a little harder to see. Your tetrahedral is like this, right? You got four of them, right? And it's three-dimensional. There's all four of them here. One of them is obscured by my hand. But all four of them, it's 109.5. They're getting closer and closer to each other. And then something sort of odd happens with the fifth one. So let me save this one. When you get up to 5 electron pairs, now what happens is the electrons start behaving more complicated ways, and they start developing structures that are combinations of the earlier ones. So let me show you this one here. What you get with this one is actually 2 angles. You get 120 and 90. So this one doesn't even have just one angle, it has 2. But let me show you the way it looks. I'm going to put the central atom here, and then I'm going to represent this with one domain coming up and one coming down. So that's your 180 degrees, right? So that's 180 degrees from one to the other. So that's a linear in a sense, right? And then let me see if I can show you how to represent this. I'm going to go out that way, and then out that way, and then like that. So what you get here are 3 in the center. I'll draw a little circle around just so you can to identify them. See how you have 3 in the middle? That's just like a trigonal planar, 120 degrees. So that's where that one's coming from. It's coming from that circle in the middle. It's an equator. Okay. And then you got the, I'm sorry, I put 90, I meant 180. And then you got your linear here, which is 180. So this one's more complicated, right? It's actually got 2 angles. It has 2 arrangements that are superimposed on each other. And I'm not going to talk much more about it, but I do want to give you the name. This one is called Trigonal Bipyramid. Okay. So again, they're moving as far away as they can. Now, technically speaking, that's not as far away as they could be. If it was, if they were all the same angle, that would be a different angle. But for whatever reason that we won't go into, these are what you get. You get two angles, and it's essentially a combination of linear and trigonal planar. And the terminology is that the electron domains in the middle, those are called equatorial. Like an equator. Now, logically, then we might think the ones on the top and the bottom are polar, but they're not called polar because polarity has to do with electrical charge. So we call them axial. So the ones on the top and the bottom are called axial electron domains, like an axis. Right? So there's one there and then there's one there. So the axial are the ones that are 180, and the equatorial, like equator, those are the ones in the middle, like a belt, right? Those are called equatorial electron domains, and those are 120, okay? Now, there's one more, and this one's easier. It's 90 degrees. So now we're at our smallest angle, right? Everything else was like 180, 120, 109.5. Now we're down to 90. That means there's more, right? And in fact, there are more of them. There's 6. So they're getting squeezed together. So this is the case where you have 6. So let me try to show you this one. So in a sense, it's like I'm going to show you like this. Okay, so this one's going into the board, this one's coming out, this one's coming out of the board, this one's going in, and then this one is coming straight up and this one's going straight down. Typically people, because it's so complicated, people will just draw it like this. Up and down, so that means vertical, up and down, and then they'll just draw it like this. And then imagine that you've got like a little square right here in the middle. So that's an equator again, right? You've got an equator, but you have 4 groups. So imagine that middle part is like a piece of paper. And so the central atom is right here at the center. And then one bond is coming up this way, one is going that way, one is going down that way, and one is going up that way. So they're coming out like a square. And then on top of that, you've got one coming up and one going down. So that's a total of 6, right? 4 corners, and then one up and one down. That's a total of 6. That one is called octahedral. And the octahedral, they're all 90 degrees. Everything's the same, 90 degrees. Okay, even these ones, again, these ones in the middle are called equatorial, just like with the trigonal bipyramid. So these ones in the middle are called equatorial. And then the ones on the top and bottom are called axial. Okay. So there's a similarity between this 5th one and 6th one. The trigonal bipyramid and the octahedral. Those are the names of those. Okay. Now what I'm going to do is I'm just going to write down a quick little table without the pictures so that you have the whole thing. So this is number of domains around the central atom. And then we're going to have the name of the shape. And then the angle. So if you have 2 domains, that would be linear, and it's 180. If you have 3 domains, that's trigonal planar, and that's 120. If you have 4, that's called tetrahedral, and that's 109.5. If you have 5, that's called trigonal bipyramid, and that is, there's 2 angles, right? There's 120 and 180. And then if you have 6, it's octahedral, and that is 90 degrees. Okay, those are the 5 that we're talking about right now. And this is based on the number of domains around the central atom. Okay, so let me see if I can, I'm going to stop the share here. Let me just come up here and see if I can do this. I would like to see, for you to see some pictures. Shapes of molecules. There we go. That's not a very good picture, I'm sorry. Sometimes these pictures, when I first look at them, they look good, and then you bring them up and they're not. Because they're scanned into the internet and it's just low resolution. Let's see. Okay, so let's do this one. Okay, so let me see if I can make this a little bit bigger. Here we go. Okay, so take a look at this one. So the one at the top, that's where you have 2 electron domains. And notice they're representing the electron domains as orbitals, right? Like atomic orbitals, like a p orbital or something like that. We're going to talk more about orbitals in molecules later. And so when you have 2 of those domains, they're as far apart as they can be as linear, and that's 180 degrees. Okay. Now notice it says in the table predicted bond angle, because even though we have this Vesper theory, it's not always correct. It actually makes some bad predictions at times. It's not a perfect theory, and not everybody uses it, but it is a relatively standard theory of shapes. The second one is when you have 3 domains around the central atom, and the central atom there is the one in the middle, it's orange, and then you have 3 domains around it. So it could be a lone pair, could be a single bond, could be a double bond, but those are the domains. 3 of them, that's called trigonal planar, and it's 120 degrees. Okay, that's the predicted bond angle. Then you get to 4 domains. And 4 domains is now 3-dimensional. So that's the first one that takes up 3D. And so the term tetrahedral actually doesn't refer to the number of domains. Tetra often means 4, right? It's the Greek letter or Greek name. It's really, the term comes from solid geometry, which the Greeks worked on, right? So if you have essentially a 4 different faces. So think of like a die. If you're playing dice, you got 6 faces. If you have 4 faces, it's called a tetrahedron. So in that picture, you can see there's a little, they drew a little, almost like a little pyramid in the middle. You see that? So that pyramid has 4 faces on it. So it's a tetrahedron, and the angle is 109.5. Okay. Now, when you get up to 5, that's our trigonal bipyramid. Here they call it bipyramidal with an AL at the end. Different textbooks will change the name slightly. They may put AL at the end. Surprisingly, it's not completely uniform. Even after 50 years of this theory, different authors will slightly modify the name. Okay. Also notice they put 90 and 120. They don't put 180 and 120. That also depends on the textbook you're looking at. The reason it's 90 and not 180 is they're just going from one of the axial down to the equator. That's 90, a right angle. But if you go from the axial all the way down, then it's 180. So you'll see it as 190, I'm sorry, as 120 and 90 as well. That's your trigonal bipyramid or bipyramidal. And then the last one, that's your octahedral. And again, octahedral, because it has 8, octa means 8. So it has 8 faces. So there's 1 here, 2, 3, 4 on the top, and then 1, 2, 3, 4, 4 on the bottom. So that adds up to 8 faces. Remember, a die has 6 faces. This one has 8. So that's why it's called octahedral. It doesn't mean there's 8 electron domains. There's only 6 domains, but they form 8 faces geometrically. So it's just a connection to the terminology. So they're all 90 degrees, right? So 90 from axial to equator, 90 from equator down to axial at the bottom, 90 from axial to the next axial, 90, 90. They're all 90 degrees, okay? So that's essentially the Vesper theory. Vesper theory says that these electron domains are going to repel each other and move as far apart as they can, and you're going to get these 5 different shapes, 5 different arrangements of electron domains. Just be careful when you're counting them. So let me show you an example. Okay, I'm going to stop share there. Let's come over here. Okay. So what I'm going to do is I'm going to give you a Lewis structure. And then we're going to count domains. So let's do this one here. Okay. So this is water. This is a Lewis structure for water. We're going to count the number of electron domains around the central atom. Okay. Well, a lone pair counts as 1. A lone pair counts as 1. So now we have 2. A bond to another atom counts as 1, a single bond in this case. Oops, sorry, 3. And then a single bond to another atom, that's 4. So we have a total of 4 electron domains. Let's try another one. Okay. So now let's consider it from the perspective of the carbon. How many electron domains does the carbon have? Technically, there's no central atom here, right? Because if you have 2 atoms, neither one can be the center. But we'll do it from the perspective of carbon. We have a lone pair, so that's 1. And then we have a triple bond, so that's 2. So the carbon has 2 electron domains. Let's try carbon dioxide. Okay, we're going to do the central atom now. The carbon atom is the central atom. It has a double bond to one of the oxygens, so that's 1. And it has a double bond to another atom, so that's 2. So the carbon has 2 electron domains. Okay, so now if we know the number of domains around the central atom, we can use that table to figure out the geometric arrangement of those electron domains, right? Linear, trigonal planar, tetrahedral, trigonal bipyramid, and then octahedral. So let me show you a couple of examples of that. Okay, so let's do the Lewis number of electron domains, and then your shape. Okay, so let's do carbon dioxide. Okay, there we go. All right, number of electron domains. We just did that one. It's 2, right? There's a double bond and another double bond, so that's 2. Don't count the lone pairs on the oxygen. They're not on the central atom. You're only looking at it from the perspective of the central atom. So ignore any lone pairs that are on different atoms or bonds that are not to the carbon. If it's 2, it's linear. And so using that sort of picture that we just saw where they had the central atom in orange, it'd be sort of like this. These are your electron domains, right? It'd be something like that. Okay, they're far apart as they can get. Okay, let's try another one. Let's try water. So here's the Lewis structure for water. Now this one we said has 4 electron domains, right? Because you have 2 lone pairs and 2 bonds, so that's 4. When you have 4, that's tetrahedral. So now this is a little harder to draw, right? But it is possible. Let me show you this way. I'm going to do it like this. Okay. So that one down here is coming out of the board, and the one back there is going a little bit into the board. Okay. So there's your shape there. Let's try another one. Let's do HCN. Okay. So carbon is the central atom. That's the one you're looking for, the central atom. It has a single bond to the hydrogen, so that's 1 electron domain. It has a triple bond to the nitrogen, so that's a 2nd domain. So it only has 2. All right. Even though that's a triple bond, it only counts as 1 domain. They're all in the same direction. They're all pointing toward the nitrogen. Okay. So that's linear. Okay. So HCN is linear, which means that the central atom is right here. And then it has a domain coming off to the hydrogen, and then a domain coming off to the nitrogen. Okay. So this is going towards the hydrogen, and this is going towards the nitrogen. This is right here is the carbon in the center. Okay. So notice with Vesper theory, with the Vesper model, a triple bond, you treat it just like a single bond or a double bond. They're all treated the same. In fact, a lone pair is treated in the same way. Okay. Let me do one. Let's do one with a lot. Let's do one with a lot of, or more, I should say. Let's do sulfur. So I'm going to draw the Lewis structure for sulfur hexafluoride. I would talk more about this molecule because it's a fascinating molecule, but we don't really have time. So here's sulfur hexafluoride, 3 lone pairs on each fluorine. And the reason that you need to do the Lewis structure first is that gives you the arrangement of electrons so that you can figure out how many domains the central atom has. So it starts with the Lewis. You draw the Lewis first. Once you get the Lewis structure, then you count the domains around the central atom. Okay, so that's our first step. The domains around this, again, forget the fluorine. The fluorine has 3 lone pairs, but they're not central atoms. It's only the sulfur that's important here. The sulfur has a total of 6 bonds to 6 different atoms, right? So it has 6 electron domains. Okay. That we said was octahedral. When you have 6, that's octahedral. Okay. So this one gets kind of tricky to draw, right? You have your central atom, and then you have 6 of these electron domains. Okay. So these are the 4 that are in the middle. These are your equatorial. And then these are the ones coming up and going down. Those are the axial, right? These are the axial, and these are the equatorial. Okay. So Lewis structure, count domains around the central atom, and then you have that chart. You need to memorize that chart. Okay. Now, thus far, all we've done are the electron domains. Now we want to do the shapes of the molecules because that's our goal. What's the shape of the molecules, not the domains? We don't, in a sense, care that much about where the electrons are. We care where the molecule, where the atoms are, so we know the shape of the molecule. An enzyme works by having this complicated shape that a little molecule called a substrate goes in, they interact with each other. So if the enzyme has a different shape, the molecule can't go in. Or if it has a different shape, some other molecule might be able to go in, right? So the idea is the shape of the atoms, not the electrons, although the electrons are important. So this gets us to the last step here. How do we go from the shape of the electron domains to going to the shape of the molecule? Okay, so here's what you do. Okay, first, draw the Lewis structure. 2, count your electron domains. Okay, 3, predict shape of the domains. 4, attach surrounding atoms to the ends of the domains. And then step 5, that's the last step, use the chart to get the shape of the molecule. I'm going to show you that chart in just a moment. So let's try an example. Actually, I'm sorry. Let me give you the chart right now. Here's your chart. Sorry. Okay, so here they are. Whew, that was a large chart there. So this chart's also in your textbook. You can find it in your textbook. It's in section 9.1. So there's a chart given for this, but I wanted to write them down for you to see them here. So here's the chart. The idea is essentially central atom is A, 2 surrounding atoms, X2. That's going to be linear. Central atom A, 3 surrounding atoms, that's going to be trigonal planar. Central atom, 4 surrounding atoms, tetrahedral. These are the shapes of the molecules now, not the electron domains, but the molecule, the atoms around the molecule. Central atom, 5 surrounding atoms. Central atom, 6 surrounding atoms. So this is just like we learned, right? It's the same as the number of electron domains. That's the same table we already did. But now what we're claiming is that the structure of the molecule is actually going to be the same as the structure of the electron domains, the arrangement around the central atom. But now notice this second part over here on the right. notice they all have E, E or E2. E means you have a lone pair on the central atom. And E2 means you have two lone pairs on the central atom. That's how that part of the chart differs. What happens is if you have a lone pair, which we represent as an E, that changes the shape. If you have two lone pairs, that changes the shape. And now we have new names. These are names I haven't given you before. Bent, trigonal pyramid, and square planar. These are new names. These are new shapes, okay? So what you're going to do is these 5 steps. You draw the Lewis structure, count the electron domains. Predict the shape of the electron domains, okay? 2, 3, 4, 5, 6. Linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. Then use this chart with the surrounding atoms. If you have 2 surrounding atoms and 1 lone pair, that's bent. If you have 2 surrounding atoms and 2 lone pairs, that's also bent. If you have 3 surrounding atoms and 1 lone pair, that's trigonal pyramid. If you have 4 surrounding atoms and 2 lone pairs, that's called square planar. Okay, so let me show you examples. Here's 2. H2O and ammonia, and H3. So H2O is water, and H3 is ammonia. 1, draw the Lewis structure. Oops. Count your domains around the central atoms. There's 4 of them, 2 lone pairs and 2 bonds. So you have 4 domains. So in terms of the electron domains, that would be tetrahedral, right? And then I said, attach the surrounding atoms to the domains. Just pick 2 of the domains, okay? So let me show you what I mean by that. So here's your oxygen at the center. You've got 4 domains, tetrahedral. Let me just bold that in. There's your central atom. Attach these 2 hydrogens to any of them. So right here, there's your H, and there is your H. Okay, I just attached them. Now you use that chart. The chart says if you have AX2 and you have 2 lone pairs on the central atom, that's called bent. Okay. Well, what does bent mean? Bent is a very simple shape. It's just V shape. Looks like this. Okay, like a V. It's called bent. So linear, bent. So here's what's happening. The atoms, the surrounding atoms, are attached to these electron domains right here and right here. So the shape of the molecule is going to reflect the shape of those electron domains, which is tetrahedral. But when we name the shape of a molecule, we're not interested in the domain, the electron domain angles. We don't care about the electron domain angles. We care about the angles between the surrounding atoms and the central atom. So here's what happens. This angle from one surrounding atom to the next, it's going to be reflective of the tetrahedral. Okay, so it's going to be an angle that's very similar to the tetrahedral. Well, that angle right there is close to a tetrahedral. Tomorrow we'll look at it in more detail. So we call it bent because if you take a look at the atoms, let me do it over here. You have an oxygen over here. You have a hydrogen coming off in this direction. And then you have a hydrogen coming off in this direction. Okay, So we don't want to call that shape tetrahedral because there's only 2 surrounding atoms. So we call it bent. Okay. Now let's try the second one. Here we have the Lewis structure, 3 surrounding hydrogens, 1 lone pair on nitrogen. Okay. Again, you have 4 electron domains. A lone pair is 1, a bond to each atom is 1. So that gives you a total of 4. Tetrahedral again, just like water. The electron domains are actually tetrahedral. So your nitrogen is at the center, and you have 4 electron domains. Okay, those are the electron domains. We'll represent them with little orbitals. Attach the hydrogens, pick 3 of them. Doesn't matter which one you pick, but I'm going to pick those 3 down there. So those are your hydrogens. Actually, let me draw the IH in there. Okay, so there's a bond, right? So essentially, in Vesper theory, we're thinking of the surrounding atoms as just attaching to the end of that electron domain. Could be a single bond, could be a double bond, could be a triple bond, but just attaching to the end. But notice we have this 4th one up here, right? That's going to be the lone pair, right? See how we have a lone pair here? That one that doesn't have a hydrogen on it, that's going to be the lone pair. Okay, so here's what you get. You get this interesting shape of atoms. The nitrogen is in the center, and then the hydrogens come off like this. And that's a shape that we didn't have in that first chart of electron domains. It's a new shape because it doesn't have 4, so it's not tetrahedral. It's not flat anymore like the trigonal planar. It's got to be a new name. So we're going to call this trigonal pyramid. Again, sometimes people will put AL at the end, trigonal pyramidal. Okay, so that one is a different shape than any of the other ones that we looked at. Okay, I didn't, sorry. So now let's come back. We have linear, which is 180. We have trigonal planar, which is 120. We have tetrahedral, which is 109.5. We have trigonal bipyramid, right? Again, sometimes people put AL at the end. This one was 90 and 120. Sometimes people do it that way. Sometimes people do it as 180 and 120. And then we had octahedral, which was 90. Now we have 2 new ones. Now we have what's called bent. And I just need to write it out here just so you have it. This is 2 surrounding atoms with 2 lone pairs. This angle is 104.5. It's a little different from the tetrahedral. If you have AX2 with 1 lone pair, then it's about 120 degrees. And this is also called bent. And then the last one we just did was AX3 with 1 lone pair, and that one is 107. And this is called trigonal pyramid. And again, sometimes people will put AL at the end, pyramidal. Okay, so the examples we just did, this one was ammonia, and this one was water. Okay. So tomorrow, what we'll do is we'll do some more of these because this is a lot of information. It's a lot of ideas put together. So we'll practice some tomorrow. We'll look at some of the Alex problems on it tomorrow. And if we have time, we'll get into the polarity issue. Okay. So Vesper theory is section 9.1. and we'll continue talking about it tomorrow. Okay. So have a great day, you guys. I will start working on the lab reports this week so that you can start getting some lab report grades in there. I think I might have 2 to do. And so those will start coming in this week for you. Okay. Take care.
Thank you.
Thank you,
Bye-bye.
Professor.